Morning. Okay, so I'm trying to figure out who I'm talking to today. How many people are here from psychology? So a lot of you. And are the rest from the medical school? It helps me figure out what examples I should give. Okay. So my name is Dr. Matt McBee. I'm from the Department of Psychology here at ETSU. And my talk today is Basic Statistical Analytic Approaches to Clinical Research Studies. And what I want to really focus on today is less about the technical or technocratic aspects of doing statistical modeling and interpreting the numbers, but more coming to grips with what the results actually tell us in terms of what it is that we want to get out of doing statistical analysis and helping us understand what's going on in the world. So first of all, I don't have any conflict of interest, financial or otherwise, related to the content that I'm presenting today. Okay, so what is it we're trying to do when we do statistical analysis? There's different goals that we can have. Oftentimes what if you read the literature, oftentimes it seems like what people are looking for is just a succinct description of a data set. So if I have a data set with several variables in it that measures some sort of phenomenon, instead of giving you, a huge spreadsheet, what I can give you instead is maybe a table of regression results or something like that that helps summarize what the important patterns that are found in the data. And from that point of view, statistical analysis is kind of like data compression. Instead of giving you a giant spreadsheet, I can give you a table with just a few rows in it, and that table communicates the major features of what are going on in the data set. Also, we use statistics to detect weak signals. Sometimes when you look at raw data, for example, if you're looking at a treatment group set of outcomes versus a control group set of outcomes, sometimes just looking at the data as a plot or as a figure or even in a table is sufficient to convince you that there really is a difference between the groups. You probably don't need a statistical analysis to understand that males on average are taller than females. That's a large signal. It's very easy to observe that. But oftentimes what we're dealing with in medical and social sciences are weak signals, and statistical analysis can help us determine with confidence whether those signals are actually present that might not otherwise be obvious to us. So we use it for that purpose a lot of times. But then that often begs the question of how important the findings really are. If you need a very powerful magnifying glass to even observe a difference between, say, a treatment group and a control group, then maybe the practical utility of the treatment is not that high. But maybe it is. We often talk about statistical models as a means of quantifying uncertainty, and that's really related to the previous point. What we're seeing more and more right now in the machine learning world is using past data to predict future observations. So when you go to Amazon or Netflix or something like that and you buy a product or you watch a show and you get the recommendations of what you should watch next, that's using statistical models to make predictions. That's something we should probably do more of in science, is try to make specific predictions for individuals. But we often don't use statistics for that too much in our areas. What we often are really doing is a topic that is actually taboo, at least in a lot of psychology, and I assume in medicine to some extent as well. And that is to assess causation. We really want to know, when we're doing science, we're not collecting stamps. We're trying to figure out what actually causes things to happen. Because once we know what causes things to happen, we've identified places where we can intervene, where we can change outcomes that we don't want to occur. And so I want to talk, that's the focus of what I want to talk about today, is how do we use statistical analysis to assess causation? And it's not straightforward. A lot of it depends on the design of the study that we're talking about. So when you read statistical or research design textbooks, they often make distinctions between randomized studies and quasi-experimental and observational. But I think a better organizational schema is this. You have one type of study broadly where the researcher controls exposure to treatment. Right? So if you're investigating some sort of medication or some sort of surgical treatment or something like that, or some sort of therapeutic intervention. That treatment is not available to people unless they get it from you, the researcher, or the research team. And so you can control who gets it. And in that situation, often the best way to allocate who's going to get the treatment is to use a randomized allocation process. And when you do that, you've got a randomized controlled trial. There's an alternative that you can do that is actually just as powerful for assessing causation that people are less aware of. That's called the regression discontinuity design. And I just want to take a poll of the room. Who's ever heard of that? Anybody? All right. One person. It's a very underutilized design. Economists are starting to rely on it almost as their bread and butter analytic technique. But even though it's been around since the 60s, it hasn't penetrated really well into the biomedical and social sciences areas. But I'm going to talk about that. So then there's this other category which is related to the first category. It's where you try to control who gets the treatment, but you can't perfectly control who gets the treatment. So we had a student in psychology that was investigating the impact of journaling and randomly assigned people to do journaling 3 times a week for 6 weeks. Well, as you can imagine, some people did that were told to do it, but some didn't do it. And that can happen a lot of times in longitudinal studies in medicine. You may randomly assign people to some sort of a dietary intervention, but they don't do it. They may not exercise. They may not take their medicine. They may not show up for appointments. And so sometimes those are called randomized encouragement trials, where you have a set of subjects. You randomly assign who you tell to do the treatment and who you tell to not do the treatment, but you can't actually enforce that decision. And so people that you assign to treatment may not actually participate in the treatment. And sometimes people in the control group may seek out the treatment. You know, if you're investigating some sort of dietary intervention, some people in the control group may decide to go on a diet. And you can't really stop them from doing that. So sometimes we call those broken randomized controlled trials, where you don't have complete control over who gets the treatment. There's also a version of the regression discontinuity design that I'll talk about later that's called the fuzzy regression discontinuity. And it's the same kind of issue where you've assigned certain people to get treatment, but they don't always comply with their treatment assignment. And then there's this last category, which is the most problematic one, where you don't control treatment assignment. And so that's where we get into things like observational or correlational studies, where you simply observe variables and you can measure their relationship or their association. But what you really want to know is to what extent one variable causes the other one. So the difference really between that and the quasi-experimental design is simply that in the quasi-experimental framework, the variable of interest is categorical. So it's group membership, so maybe smoking versus non-smoking. Whereas in observational, or correlational, there we go. In correlational research, the context is usually continuous variables. But they're confronted by the same set of issues when it comes to assessing causation. So how do we go about doing this? Let's first start by a working definition of causation. Now you could spend years of your life reading philosophy about what actually constitutes causation. And I don't want to get too deep into that because it's a deep area. We can settle on a functional working definition for causation that is good enough to help us discuss these issues. This is promoted by Pearl et al. In his monograph on causation. We can say that X causes Y if Y depends on X for its value. That's a really simple way to talk about causation. The idea being if X causes Y, and that's what's denoted by the arrow, if we change X in some way, if we intervene on X, we alter X's value, we expect Y to change to some extent. It may not be perfectly linked. There may be other causes of Y. We're not saying here that X is the only thing that affects Y. But if we manipulate X, we should expect Y to change, but not the opposite direction. Right? If this is the case where X truly causes Y, if we change X, Y should change. But if we change Y, nothing will happen to X. Right? That's just how this definition works. So if we can agree that this is a good enough definition of causation, we can move on. Now, I think everybody knows this. At least I hope you do. It's sort of a mantra, at least in psychology. Correlation does not imply causation. You can observe that variables are related to each other. That does not constitute proof that one variable causes the other one, right? I mean, there could be lots of reasons why things are related to each other that don't have to do with causation. So, some people will say, oh, okay, I understand this, but I don't do correlational research. I only do quasi-experimental research. Well, I got bad news for you. Every statistic that you could derive from a statistical analysis, whether that is a group mean difference between, say, a treatment and control group, whether that is a regression coefficient, whether that is an odds ratio, all statistics are fundamentally equivalent to correlations. They can all be transformed into correlations. So, for example, Cohen's d effect size, which is a standardized mean difference, that's just a correlation in disguise. An odds ratio, a slope coefficient, an ANOVA eta squared, they're all fundamentally correlations in their heart. Everything is a correlation. And what that implies is that since correlation does not imply causation, no observed statistic implies causation, right? A group mean difference doesn't imply causation. It could indicate causation, maybe in the context of a randomized study, but if you simply look and note that smokers don't live as long as non-smokers on average, that doesn't necessarily prove that smoking is the reason why that happens. So this is true for all statistics that you could think of. So this isn't just a problem that affects correlations. This is a problem that affects every statistic and its interpretation. So the flip side of the statement that correlation does not imply causation, causation does imply correlation. You know, if one thing causes another thing, then those two variables will be correlated under almost all circumstances. I have an asterisk there because there is one weird circumstance where that might not happen, simply because correlations are measuring linear association only, and it's possible you could have a nonlinear association between variables that the correlation would detect, but that's kind of in the weeds. You can ignore that star. We'll just ignore that case. That's a corner case. So yeah, causation does imply correlation. And what that means is that correlation sometimes implies causation, and sometimes it doesn't. So when you observe that smokers don't live as long on average as non-smokers, that might mean, it could be the case, that smoking made that happen. But it's not necessarily the case that smoking made that happen. So, we have three formal frameworks for discussing causal inference in the social and biomedical sciences. There's the threats to validity framework. People talk about Campbell and Stanley. I'll show you in a second. This is sort of, the threats to validity framework is the classic way of talking about this. Dates back to the early 1960s. If you've ever, I mean, who's heard of it? Who's been trained this way? If you've had a research methods class or something and they talk about different threats to validity, could you raise your hand? Okay. Is this common in medicine? I don't know. It's common in psychology. Medical people talk about this? Okay. It's still, in our textbooks, I think it's still treated as the kind of standard, which is unfortunate because there are much better and more modern ways of thinking about causation that are more complicated but also create a lot more insight. So maybe medicine's moved beyond this one. We also have this thing called the potential outcomes framework, which is sometimes called the counterfactuals framework or Rubin's causal model. And is that something that medicine uses a lot, where you think about what's the counterfactual? If you treated this patient, what would have happened to them if they had not been treated? The difference between those two things is how we formulate what causation is in that framework. And then finally, there's this causal diagrams perspective that's attributed to Judea Pearl. These things are also sometimes called directed acyclic graphs, or DAGs. My students know I love DAGs. DAGs, I know, are really influential in epidemiology. I don't know about other aspects of medicine. But I'm going to run through these just very briefly and talk about their strengths and weaknesses. So the first one is the threat stability framework. This classic book. It's less than 100 pages long, and you can get the full text of it free online because it's out of copyright, by Campbell and Stanley. It's a really interesting book to read, and it's a quick read. Maybe if you're going to the beach, you know, throw it in there. It's good beach reading. But their definition of causation, it doesn't actually say what causation is. It says what causation isn't. So it's a negative definition of causation. Causation, in their framework, causation is what is left over after you eliminate every other potential explanation. So, for example, if you observe that two variables are correlated or two groups are different, then you can start running through these alternative explanations for the difference that are non-causal. So, for example, history effects is one of the threats to validity. And that is, if you can't read the text, occurrence of outside events during the course of the study. So maybe I'm sampling, I'm trying to find out how people feel about gun control or something like that, and I measure a bunch of people's opinions, and then the Parkland shooting happens in the middle of the study, and that changes people's opinions, right? And so that's an example of a history effect. Something that happens during the study that changes how people's responses come out. So there's these other threats. Maturation. People naturally get better at certain things with age or get worse at other things with age. So if you're tracking students over time and you note that, you know, the 5th graders could read this well, but then when they got to 6th grade, they could read this well, that might simply reflect their natural maturation process. It might not reflect anything that you did or anything else. So there's testing. Some of these are kind of technical. Instrumentation, regression to the mean, which is one that nobody ever thinks of. But the big one, experimental mortality. That doesn't necessarily mean that your participants died. It could mean that, but it just means that they dropped out of the study. And you do see this sometimes in medicine and in psychology, where some people have a bad reaction to the treatment. You know, maybe you're investigating an antidepressant medication and it makes some people feel suicidal and they think, I've got to stop taking this. This is not good for me, and they drop out of the study. And so you make your inferences based on who's left, and you don't have those people's information. That can be a threat to validity. But the big one here that's kind of buried is this, what they call the selection threat. And that is, there could be systematic differences between subjects assigned to groups. And that's really the threat that's most important. These other things are kind of details, but this one is also sometimes known as confounding. You heard that term before? Okay. So if you have a perfect randomized controlled trial, you know there's no selection threat because the treatment arm and the control arm are equivalent in expectation, right? There's no systematic differences between groups when you created the groups by flipping a coin. But as soon as you have imperfect compliance, or you're in an observational context where you did not control allocation of treatment, or if you're in a regression discontinuity design context, that could be a big problem. So really these other theories of causation are describing what to do about the selection effect, the selection threat. So it's kind of, I view this framework as legalistic. You know, it's like if you could rule out beyond a reasonable doubt that any of these threats are responsible for what you're observing in the data, then and only then can you conclude that there's a real causal effect going on. But that's not super helpful because it's not very rigorously laid out. There's no mathematical framework behind it. It's a lot better to be able to affirmatively say what causation is instead of just saying what it isn't. And so that takes us to the potential outcomes framework. This has a pretty interesting history. Donald Rubin is a statistician who I don't know if we would say discovered or invented this framework. But before doing this, he had done a lot of work on missing data. And it figured out how we can do proper statistical inference even when some of our observations are missing. And what he realized is that this issue of causal inference is simply a missing data problem in disguise. And I'll show you why that is in just a moment. And so his insight was that essentially we can apply the same tools and techniques that we use to understand missing data to understanding causation, because it's the same problem. So this is a mathematical framework with its own notation. And once you get your head around it, the notation's pretty simple, but we probably don't have enough time together today for you guys to develop like an intuitive, easy reading of this stuff. But what we have to distinguish, the core idea is we've got to distinguish between. So we have this variable in this framework is usually denoted a D, which is treatment status. D equals 0 means you got control. D equals 1 means you got exposed to treatment. And I would say that the treatment can be very, it can be anything. The treatment could be graduating from high school. The treatment could be smoking. The treatment could be exposure to early childhood trauma. It doesn't necessarily have to be a treatment in the way that we think of something that we would assign to somebody in the context of a randomized study. The treatment is simply the variable whose effect we're investigating on the outcome. And it is assumed in this framework to be dichotomous, so one of two levels. So D equals 0, D equals 1. So every subject is either in treatment or control, right? They were either exposed to the thing we care about or they weren't exposed to it. But at the same time, every subject has two potential outcomes. The outcome variable is denoted by a Y. Y0 is the potential outcome under control. And Y1 is the potential outcome under treatment. And one of the core insights of this model is that everybody has both. There's something that would have happened to you if you were exposed to treatment. There's something else that would have happened to you if you were not exposed to treatment. And both of those things can be said to exist in some way. And the way causal effects are defined in this potential outcomes framework is as the difference between the potential outcomes. So if I want to know what would be the causal effect on you of getting a flu vaccination this year, the only way I can truly know that is to know what would have happened to you if you had gotten the vaccine minus what would have happened to you if you had not gotten the vaccine. So every person, the little subscript I indicates something that varies over individuals. In Rubin's framework, every individual has their own causal effect, and it can differ, right? And we know this is true. Like, some people have big benefits from certain medications. Other people don't experience any benefit. Others could be harmed by the same medication. So everybody has their own unique causal effect. What we can estimate in our studies is something called the average treatment effect. So I know it's almost lunchtime. That does not mean we're going to eat something. It simply stands for average treatment effect. And what that means, if you're not familiar with this notation, the E means expectation. And expectation just means take the average. So the average treatment effect is the expectation of each individual's individual causal effect. So we're averaging over the effect of treatment for all the people. And that is the quantity that we can estimate from things like randomized controlled trials. When we look at the mean difference between the treatment group and the control group, that's an average treatment effect that we can estimate. And the way we calculate that is the difference between the potential, remember Y1 is the potential outcomes under treatment, and Y0 is the potential outcome under control. So the way we calculate this treatment effect is we take the average of everybody's potential outcome under treatment, and we subtract the average of everybody's potential outcome under control. That difference is the causal effect of treatment. So if we're trying to investigate, for example, how much does Prozac reduce depressive symptoms, right? This is what people's depression would be if they took Prozac. This would be what their depression would be if they didn't take Prozac. The difference between those two things is the causal effect of Prozac, right? The average effect across all the people. Make sense? Anybody questions or anything about that? The notation is kind of thick with this stuff, but the ideas are pretty intuitive. So here's the fundamental problem of causal inference. As identified by Rubin, we have laid out our definition of a causal effect as the difference in potential outcomes. But we only get to observe one of the potential outcomes for each subject. So for example, remember D tells us whether they were actually in treatment or actually in control. So this row is the people that were in the control condition. For the people that were in the control condition, we get to observe their potential, we get to observe their potential outcome under control, right? We don't get to observe their potential outcome under treatment because they didn't get the treatment. They only got the control. So we get to see this cell that's marked observable. For the people in the control condition, their potential outcome under the other condition is called the counterfactual. What would have happened to them if they had been in the treatment group? We don't know. Okay? And the same is true for the people in the treatment group. For the people in the treatment group, we only get to see their potential outcome under treatment. We don't get to observe what would have happened to them under control. And you might think, well, what if we just gave them the treatment and then gave them the control? I mean, that doesn't get around this problem because there can be carryover effects. You know, maybe being exposed to treatment first affects what people's potential outcome will be later. So in our universe, since we don't have a time machine or any access to a parallel universe, we only get to observe one potential outcome for each group. And the problem is our way of defining the causal effect, you know, to know what the expected value is for people in control, we need both of these. We need a contribution from both of these, but we only get to see one of the two. And the same is true for that one. So that's the fundamental problem of causal inference. It's a missing data problem. So when can we actually interpret a group difference as a causation, as a causal effect? There's a condition where we can do that that's called ignorability. Treatment assignment is ignorable when the potential outcomes are independent of the treatment. In other words, if the potential outcomes are not altered by exposure to treatment, then we can look at that difference in outcomes between the treatment and control groups, and we can interpret that as causal. So when does that actually happen? When does ignorability occur? Well, if we have randomly assigned people to treatment and control, then we know that there can be no systematic pre-treatment difference between the treatment and control group, right? Because those groups are created by a coin flip. What that means is the treatment and control groups are equivalent on all background variables, including the potential outcomes. And that is why randomization works, according to Rubin's perspective. Randomization creates ignorability. But we can create ignorability in a different way. If we don't have ignorability to start with, what we can do is we can achieve what's called conditional ignorability. Conditional ignorability means that if we can identify those background variables that are different between the treatment and control groups, so that's what's being denoted by the bold X. You can think of X as a matrix that includes all the different background characteristics that we think are important. So for example, if we're trying to understand why smokers have shorter lifespans than non-smokers, so D is smoking status. Well, what other things are different between smokers and non-smokers that could cause their lifespans to be different, even above the fact that some smoke and some don't? Like, what things come to your mind? How are smokers different? Income? Yeah? Yeah? Smoking is more likely to be found for people that are low income, low SES. And being in a different SES category has consequences, right, for your lifespan. So what else? COPD, exactly. So there's lots of things that could be different systematically between smokers and non-smokers. If we can figure out what those things are, if we can identify those variables, X, and we can condition on them. And what I mean by condition on them is hold them constant in some way. In other words, if we can make sure that there's no variability on those other variables, then the only difference left between the groups that matters is that some smoke and some don't. And if we can achieve that condition, then we can observe the different outcomes for those two groups, and we can interpret that difference as causal. So that's what Rubin means by conditional ignorability. Conditioning is just a word that means to hold constant. Now, how can we hold things constant? I mean, one way would be to simply, like if we think that SES, or socioeconomic status, is important, maybe we're only going to sample people within one strata of SES. That's one way of holding it constant, so that our sampling process holds it constant. That's one way to condition. But the problem is, if we have multiple variables, I keep doing that, if we have multiple variables, we're only going to sample people at a certain SES, and we're only going to sample people with a certain level of COPD, and we're only going to sample people with a certain level of education, pretty soon we have a very sparse sample. We're going to have to reject almost everyone that shows up to be in our study because they're not going to meet our inclusion criteria. It's too restrictive. And so what we use instead of sampling most of the time is we use statistical models to accomplish virtual conditioning. That's one thing that statistical models do very well, is they allow us to examine what would have happened if we could hold certain variables constant. That's the real virtue of things like regression and logistic regression and things like that when we're trying to understand causation. They allow us to efficiently condition on more than one variable at a time. So, as long as we can achieve conditional ignorability, we can interpret a correlation as causal. We can interpret a group difference as causal. We can interpret an odds ratio as causal. So, one very common method that you see in medicine and psychology for doing this kind of conditioning is using a statistical model called linear regression. And how does that work? Well, I don't want to get too much in the weeds, but the idea is that we have a response variable, and we include our treatment variable as one of the predictors, but we also include in the model the other variables that we want to condition on. So if we're looking at the difference between smokers and non-smokers, maybe C represents lifespan, maybe A represents smoking status, and maybe B represents socioeconomic status. Right? We want to condition on socioeconomic status. In the regression model, the way the interpretation works is that the effect of A is computed as if B had been held constant. And the effect of B is computed as if A had been held constant. So in this example, I have a regression table. It's okay if you've never seen one of these before and are not comfortable reading them. What we have here, this is the this line right here is the effect of A, and you can see that its estimate is almost 0, and its p-value, it's okay, is non-significant. What that implies is that after conditioning on B, A is not associated with the outcome. So how does that work? Here's how it works. Picture's worth 1,000 words. Yeah? I'm joking. Okay. So what we have here, this is how regression works. In this case, this is a pretty basic regression model because there's only 3 variables. There's an outcome. There's 2 predictors, A and B. So what we have is a 3-dimensional space, essentially. On this, what we call the z-axis, the height of the points represents their level of the outcome variable. So that could be life expectancy or something like that. And then along this dimension, we have their values of A, and along this dimension, we have their values of B. And what the regression model is doing, when we get this table of regression coefficients, you see that there's an intercept and there's actually a slope for A, which tells us how sloped is that surface along the dimension of A, and there's one for B. What it's actually doing is it is finding the shape of a surface that best passes through that cloud of points. And that's what you see, that grid. That grid is the regression surface. And the points are kind of arranged around it. Some points are above the surface, some points are below it, but that surface was created such that it falls as close to the points as possible. So once we have that regression surface, how do we isolate the effect of one variable while holding the other one constant? Well, that's what I'm trying to show in this figure. If we have these points in space, what we can do is we can rotate that whole object so that we're looking at it down here. We're looking at that object along the dimension of B. So it's like we're here and we're looking this way. If we turn that thing just right, we're looking right along the edge of that regression surface, and we have something that looks like this. And now it looks like there's a line. And we can describe the slope of that line. That is this value. That value is telling us the slope of the regression surface with respect to that predictor variable. So when we orient the regression surface in this way, you can see that this dimension is B and this one is C. Any variability on the other variable is like into the page. You know, it's been rotated into a dimension that doesn't matter. We can isolate the slope for one variable's effect on the other by rotating the surface in a certain way. So here we can see that when we take A out of the equation, there's a strong relationship between B and C because that slope is positive. You know? If we rotate this solution a different way so that we look at it from here, you know, if our face is here and we're looking at it this way, that's what's in this panel. So now we're isolating the effect of A without worrying about variation on B. We've oriented the surface so that we can see it from that perspective only. So that's basically how regression accomplishes conditioning. It figures out the shape of a surface that passes through the points optimally. And then using that surface, you can isolate the effect of each variable while ignoring variation on the other variables. So this is far more efficient than turning away people that walk in the door unless they have a very specific value of B and a very specific value of A. This lets us use all the data and use a statistical technique to accomplish conditioning. And remember, we have to do conditioning to get to ignorability, which lets us interpret the result as causal. So, you know, this can work well, but when we do this, we're making some assumptions. One assumption we're making is that this thing really is linear. Sometimes the variables that we're studying don't have linear effects. You know, often if we're investigating the effect of a medicine, there's something called a dose-response curve. Like, you keep giving more and more medicine, depression doesn't just keep decreasing. You know, at some point it levels off. So we have to get that part right. We have to make sure that the model is, if the model assumes linearity, that has to be correct. We also have to make sure that the model is complete. It has all the variables in it necessary to achieve ignorability, that the model is correctly specified, and this is the big one, that the predictors are measured without error. That's impossible. You know, we can never actually achieve that. Perfect measurement is impossible. The best we can do is to get very precise measurement. So, I mean, we can measure a lot of physiological things very well with very high precision. We can measure blood pressure very well. We can measure blood sugar very well. But psychological variables, when you ask people how much pain are they in, and they say on a scale of 1 to 10, I'm an 8. Or you ask people how depressed they are, and they fill out a depression screener, that's quite imprecise. So in practice, it's difficult to adequately condition on those kinds of variables because they're not measured that well. The other thing is, when we use statistical models, we're sometimes really relying on the model to make extrapolations beyond where we have much data. So here's an example where we've got two little bits of widely separated points. Maybe this is a treatment and this is a control. And the model has figured out that there's a certain slope on A and a certain slope on B, but it's doing that on the basis of a very limited amount of data. the model will happily extrapolate to anywhere. It will take that regression surface and push it out across the state of Franklin, even places where there's no data. So you have to be careful about that if you use these kind of statistical models. You don't want the model to go too far beyond the bounds of where you actually have data, because then your whole, all the inferences you're making are basically very, very assumption driven and not so much informed by the data. All right, so that kind of wraps up the potential outcomes framework. The other one I want to talk about briefly is this causal diagrams perspective. And this one's kind of fun. I like it. My students don't like it, though. I don't know why. I love it. But what you do essentially, the question I think is begged by the potential outcomes framework is, how do you figure out what variables you need to control? How do you figure out what variables you need to condition on? And in this graphical framework, what you do is you transform your working theory of what variables are affecting the system into a diagram. Where you put your variables on the diagram, and then you connect those variables with arrows that indicate your hypothesized pattern of causation. So here in this left panel, let's say X is our treatment, Y is our outcome. We think that there's a variable called Z out there, which is causing people to get different levels of treatment, also causing people to get different levels of the outcome. So this is a situation where we have to control or condition on Z. But in this panel, what we have is a treatment that's happening, and then Z is part of the mechanism by which treatment works. So maybe if this is an antidepressant that we're giving people, maybe the way that antidepressant works is by altering their receptors on their neurons. And when the receptors get altered, that changes their mood or their depression. So there's that path, but there's also placebo effects. A lot of times people feel better just because they're getting some treatment. And even if it was a sugar pill, they would feel better. So that could be this arrow, the direct arrow. So in this framework, the mechanism of treatment has two things that are happening. One is by its effect on the receptors, and other is through the placebo effect. So you use theory, scientific insight, and logic to construct a diagram, proposed diagram, and then you analyze that diagram to figure out what variables you have to condition on in order to achieve causal inference. So I'm going to skip a little bit of this. Whenever you have an arrow that indicates causation exists, you also have statistical association or correlation. So here, Z causes A. That means Z and A are correlating, right? Z causes A causes X. That means X and Z are correlating. Same with Y. Well, guess what? In this diagram, you can see there's no arrow connecting X and Y. What that means is that X doesn't cause Y. Y doesn't cause X. But these two variables will be correlated because they have Z in common. Make sense? Just like if you observe in the summer that drownings happen more often on days of high ice cream sales. That doesn't mean that ice cream is causing people to drown. It means that people go to the pool and buy ice cream when it's hot. So like Z could be the weather. And X could be drownings, and Y could be ice cream. So essentially, Pearl laid out something called the backdoor criterion. And essentially, he lays out the rules that are required to achieve ignorability, though he used a different word. It's the same concept. That if we can come up with a set of variables to condition on that intercepts all the so here we have the spurious association between X and Y that's caused by Z. If we can remove that spurious association, the remaining relationship between X and Y will represent their causal relationship. So that's the backdoor criterion. And this is a regression result that I generated from this figure. So here we're doing a regression model to look at the relationship between X and Y. Now we know from this diagram there's no arrow between X and Y, so the true causal relationship here should be 0. But if we look at this result table, if you know how to read these, this line right here tells us the effect of x on y. This estimate is not 0, and it is statistically significant to a very high level. So this is a case where correlation does not equal causation. Our statistical model is telling us that x and y are associated, but that association does not measure the causal relationship between the variables. Now what happens in these diagrams, when we condition on a variable by holding it constant, we block the ability of that variable to transmit causation further. So in this figure, if we condition on A, if we held A constant, think about it. We define causation as when one thing changes, the downstream thing changes, right? Here, when Z changes, A changes. And when A changes, X would change, except we're conditioning on A, so we're not letting A change anymore. So when Z changes, A can't change, and that means no association can be transmitted to X. So when this happens, we've broken what we call the backdoor path between X and Y. And after conditioning on A, the association that we measure between X and Y would represent the true causation between those variables. Same is true here. If we condition on B, we block the ability of Z to get to Y. That will have the same effect. Or we can condition on Z. And what we can see in this table here, these are regression results from all those different models. So this is the one I already showed you, the first row. If we just look at the relationship between X and Y without conditioning on anything, we get this answer that suggests X and Y are causally linked when they're actually not. But look, if we condition on A, the estimate goes almost to 0, becomes non-significant. If we condition on B, it goes within rounding error exactly to 0, non-significant. If we condition on any set of those variables, we get the correct answer. So there's no real conflict between this framework and Rubin's potential outcomes framework. They're actually quite complementary. They don't differ in any way in terms of their substantive advice. It's just, I think the graphical perspective helps us figure out what variables we need to condition on. And there's a website called daggity.net where you can draw one of these diagrams in your web browser. And as you're drawing it, it will identify automatically what variables you have to control or condition on in order to, so everybody's looking at this like, what is that? So this is one of the pre-loaded examples on the website from a paper by Polzer et al. And what they were trying to estimate was the relationship between tooth loss and mortality. So what's the causal, how does losing a tooth change your risk of dying? Not association, but causation. What is the causal effect of losing a tooth on your risk of dying? And what they figured out is that you have to also, to answer that question, you have to identify all of these background characteristics, like how much alcohol do they drink? What's their lipid profile? Do they have hypertension? Do they have psychosocial factors? You know, and those things will be described further in the paper, I'm sure. Do they have diabetes? Are they obese? And they they created this diagram by linking these variables together with arrows based on what they think causes what. And this website automatically analyzes this thing and tells right here at the top, if you're going to estimate the causal effect of tooth loss on mortality, you have to control for one of these two sets of variables. Either age, alcohol, periodontitis, psychosocial factors, sex, and smoking, or this other one. And if you do that, if you condition on this set of variables, if you can measure all those things well enough, what's left, the association you observe between tooth loss and mortality will tell you how much tooth loss affects your risk of dying. So that's what this does. Okay. I'm a little short on time. I think we all know randomized controlled trials. You know, why do they work? We already talked about that from one perspective, but from the causal diagrams perspective, the reason that works is, let's say that these are treatment. In a randomized controlled trial, what controls your allocation of treatment? It's only one thing, right? What is it? In a randomized controlled trial, It's the randomization process, right? It's like this randomized coin flip that controls who gets treatment and who gets control. So think about the coin flip as R. That's the randomization process. The randomization process controls who gets treatment. Treatment controls or influences the outcome, but there's also probably a bunch of other things that affect people's outcomes that we don't know about. So they're unobserved. But you can see here there's no confounding. There's no way for these variables to get to treatment because we control treatment through a randomization process. And so that's why randomized controlled trials work fine. Now what about a broken randomized trial where you have imperfect compliance? Now the problem is you are randomizing people to treatment, and that's affecting how the likelihood that somebody gets treatment or not, but there's probably this other lurking variable out there that's also controlling whether they comply with the treatment assignment. You know, you told everybody in your treatment group to run for 30 minutes 3 times a week, and some of them will do that and some of them won't. Right? And the reason why some of them won't is this variable u. Now if that variable u can also affect their outcome, you have a problem here. Randomization can no longer directly tell you the causal effect of the treatment on Y. So that's what we call a broken randomized trial. There is a statistical way to recover the treatment effect from this. There's something called instrumental variables analysis. You may have heard of something called complier average causal effects that tries to get around this. Tries to estimate what's the effect of the treatment on the response variable for those that comply with the treatment status or the treatment assignment. Okay. I don't have a lot of time here, but I told you I'd talk about regression discontinuity design. So this is another kind of a design you can use if you want to figure out, if you can control who gets treatment and who doesn't. Maybe you don't want to randomly assign them. Maybe you can only treat so many people, and you want to treat the ones that are worst or that need it the most. So imagine that you have some sort of intervention for people with COPD. Instead of randomly assigning people to treatment or control, you might say, I'm going to measure your severity of symptoms, and the ones that pass some sort of threshold, all of those get treatment, and all the ones below threshold get control. And this can be really nice because it's more humanitarian. It's a more humanitarian way to assign treatment. It gives treatment to the people that need it the most. So there's this thresholding process that you use to decide who gets treatment. And the way it works, the variable that you use to decide who gets treatment is called the forcing variable. That could be a measure of severity, pretreatment severity, or something like that. And so we look at the relationship between that forcing variable and the response. And so all these dots here, the red dots, are the people that got control. Now above the threshold on the forcing variable, everybody above that threshold gets treatment. And what you will see, if the treatment is effective, there is a discontinuity in the line. That gap measures the strength of the treatment effect. So that difference right there measures the strength of the treatment effect. And this seems weird that this would work because in randomization, the treatment and control groups are equivalent on all these background variables, and that's why randomization works. But here, the treatment and control groups are quite distinct on the forcing variable. They're non-equivalent by design. So the intuition here, let me skip this. The intuition here is that if you look at the cases that are right at the boundary between treatment and control, if there's cases right at the boundary, those cases are maximally different on treatment, but they are minimally different on the forcing variable. So essentially, if we had a bunch of cases that were just, the treatment cases are just on one side of the threshold and all the control cases are just on the other side of the threshold, we could just compare their outcomes and we would be good. There'd be no problem. In reality, we usually don't have, we have cases that are more spread out, and the more spread out they are, the more we have to use information from cases far from the boundary to estimate what's actually happening at the boundary. And so what that means is we've got to do a good job of modeling that relationship, because here, this panel on the right is correct. There is no discontinuity. There is no treatment effect, but because the line's curved, see? But in this panel, if we ignore the curvature and we use a model that assumes the lines are straight, it creates the appearance of a discontinuity where there isn't actually one. And so here's another example. So that's one way that regression discontinuity can go wrong. You've got to get this model specification part right. But the thing that's good about this, it's a very graphical technique. So you can literally look at these plots and assess using your eye whether the assumptions you're making are reasonable. And so it's a really powerful technique. It lets you allocate treatment to the people that need it the most and not the ones that happen to get randomized into treatment. So closing thoughts, we're really short on time, so I think I'm going to skip this and just open the floor to any questions or comments. What do you guys think of this? The sample size, yeah. So that's considered to be a separate issue. All of this discussion is sort of leveraged on the idea that you have a reasonable sampling process, that you're not inducing other kinds of conditioning in your sampling process. So for example, in our department, we recruit a lot of college students into our studies. We are inadvertently conditioning on a certain kind of person that goes to college. They're not necessarily representative of all the community or the people that we might want to generalize to. But I think the big size, two things happen. One is your estimates are very imprecise. So it's hard for you to really say what's happening in the data because you just have so little precision. And the other thing that happens, there's a really unfortunate interaction between low sample size and publication bias in the real world that we live in, where small samples, it's quite easy to mess around with the data until you get a statistically significant finding, and then that's more likely to be published. So those are the two reasons why. If we're operating in the theoretical world, the only problem is with small samples is imprecision. But in real life, it makes it easier to find things that aren't really there and get those things published in the literature. So that's why we should be suspicious of studies with small sample sizes. Mm-hmm. That's right. Yes. Yeah, that's exactly right. So that's great. That's such a good point. The issue with regression discontinuity designs in general is that they estimate something called a local average treatment effect, which is how big is this discontinuity at the boundary you chose on the forcing variable. And it may be the case that if you set the threshold higher, the treatment effect could be a different magnitude. Or if you set it lower, it could be a different magnitude. There's no way around that in regression discontinuity. Often, in practice, what we usually do is we try to pick boundaries that are already being used so that they have some meaning. So if I want to evaluate, say, gifted education programs where students need a certain qualifying score to get in, that's where I'm going to set my boundary so that I can evaluate how effective the program is as it is set up. But you're right, if I made the boundary higher or lower, it could get a different local average treatment effect. The same is true with compliance. If you have people that don't comply with treatment, the treatment effect you're estimating is for the compliers. The people that didn't comply with the treatment may not experience the same benefit or harm that those people did. Any other questions or comments? Okay, I'll take that as a no. Thank you very much.